Okay, so this is the last section of chapter 4 that we're going to be looking at, 4.9. We're talking about solving systems of linear DEs by elimination. And systems of linear differential equations is a much bigger subject than we're able to talk about right here, and we will explore it in much more depth in a later chapter. It's going to be towards the end of this course. We look at these systems in more depth. But this is one technique that we could use to solve these linear DEs, and it mimics what you do when solving different systems of equations in algebra using a technique by the same name, elimination. So before we get into that, we need to talk about how we're going to represent our differential or our systems of equations before solving them. Here's an example of a system of two differential equations, linear differential equations. X and y in these equations are thought of as functions of t. Okay, so the first thing you want to do is get all of your x's and y's as well as all of their derivatives, second derivatives, and so on, all over to the left-hand side. And then get any functions of t to the right-hand side of both equations. So that's what's going on here. We've taken anything involving an x or a y or any of their derivatives, moved them over to the left, and that's what you're seeing here. I'm also being careful to keep all of the x's together and all of the y's together like this. Okay, next thing I want to do is rewrite the left-hand side of each of these equations in operator notation. So remembering operator notation, I have x double prime plus 2x prime minus x here. These three x and x's with their derivatives can be written in operator notation this way: d squared plus 2d minus 1x. Okay, same thing as this, just an operator notation. Y double prime minus 3y is the same thing as d squared minus 3 operating on y, and the sine of t is just sine of t. And then I did something similar down in the second part right here. Okay, we need our equations to be in that operator form to do what we're going to do when solving these systems. And I'm not going to walk through a general format or technique or derivation or anything like that for solving using elimination. It's best to see how it's done just by looking at examples. And we're only going to look at 2 examples in this section. Okay, so let's start with this one right here. I have this system, dx dt equals 4x plus 7y, dy dt equals x minus 2y. All I have are x's and y's and their derivatives, so everything gets moved over to the left in both equations. This becomes dx dt minus 4x minus 7y equals 0. Here I'm going to move everything over, and I'm going to make sure that my x terms appear first. So that x gets subtracted over and gives me a negative x. And then I'm going to have plus dy dt plus 2y equals 0. Okay, now in operator notation, this is the same thing as d minus 4x minus 7y equals 0, and negative x plus d plus 2y equals 0. Okay, now here's where we start to use this elimination technique. Once I've gotten this into operator notation the way that I have. If you remember from algebra, when you want to solve a system of equations using elimination, the goal, as the name implies, is to eliminate one of the variables in that system of equations. And you do that by taking your 2 equations and trying to get a common coefficient. Or actually, the way I do it is I get coefficients that are opposites of each other. So here I have a d minus 4x. I would like for this guy to have a negative d minus 4x, because then what's going to happen is if I add these 2 equations, those guys will cancel each other out, leaving me with just y's to worry about. So in algebra, what you're doing is you're multiplying both sides of an equation by a number to do that. In differential equations, we're operating on both sides of an equation using a differential operator. But differential operators, as we've seen, obey a lot of the same properties as multiplication. In fact, for the purpose of working with them, you can just think of it as multiplication when you're simplifying and doing that kind of stuff. So what I'm going to do is operate on both sides of this equation right here, the second equation, by d minus 4. So that gives me this. My top equation is still d minus 4 minus 7y equals 0. My bottom equation becomes negative d minus 4x. Notice I just operated on this by d minus 4. And then the negative, again, because it's kind of works the same way as multiplication, I can think of that as a -1, which can come out to the front. Plus, this second term is being operated on by a d minus 4 as well. So it becomes d minus 4, d plus 2y. And then here, 0. Remember, any differential operator applied to a 0 is still just 0, because 0 is its own derivative and all of that. So that second equation becomes this. Now what I'll do is add these two equations. I forgot my x there. And you notice I get a cancellation with these two x terms, leaving me with the following. Now this guy right here, I'm going to expand this out. And again, you get to think of this composition of differential operators as multiplication. You can actually FOIL this thing, even though it's technically not the same thing as multiplication. It still works. So what I'm left with now is -7y plus, this becomes d squared minus 2d minus 8y. Okay? And that's equal to 0. Now what you could do is bring the y in to each of these individual operators in parentheses here. And you notice one of the things I'll get is a -8y. And I also have this -7y. Those are like terms. You can combine those, and they would give you -15y. So let me actually just change the way that this looks. I'm going to write that as d squared minus 2d minus 15y equals 0. That's fair enough. I can do that, right? What is this, though? This is a second order linear differential equation. It's homogeneous and it has constant coefficients. This is something that I know how to solve using the techniques that we talked about back in 4.3. And so I'm going to do that. I'm going to solve this thing using those techniques. Notice, because it's an operator notation, I have the form of my auxiliary equation right away. M squared minus 2m minus 15 equals 0. This thing factors to m minus 5 times m plus 3 equals 0, which gives me m equals 5 or -3. Okay, so that right away I have a solution for y now. Y of t is equal to what? C1 e to the 5t plus c2 e to the -3t. But it's important to remember that we are talking about a system of differential equations here, which means that we have two functions that we're solving for, x and y. I've only got one solution. So now I need a solution for x. And what I'm going to do, instead of just taking, my answer here and substituting it in for y like you kind of would normally do with a system of equations in algebra, I'm actually going to do elimination a second time, but this time intentionally eliminate the y's, leaving x's left over. Okay, so let's take my system of equations again up here, and my goal now is to eliminate the y term. So notice I have a d plus 2 showing up here and a -7 showing up here. What I'm going to do is operate on the top equation by d plus 2, and the bottom equation I'm going to multiply everything by 7. So what does that look like? That's going to look like this. D plus 2, d minus 4x minus 7, d plus 2 equals 0. And then multiplying everything on the bottom by 7, I get -7x plus, it's +7 I'm multiplying by, plus 7 times d plus 2y, I forgot my y there, equals 0. That's going to cause these two terms to eliminate when I add them together, okay? And we're going to multiply things, we're going to expand these out, thinking of it similar to how we think of multiplication. D squared minus 2d minus 8 x minus 7x equals 0. Notice that this is the same thing that we got in the previous case, but with an x instead of a y. So I'm expecting this thing to solve in a very similar way. And noticing that this is giving me essentially an identical equation to what I had up here, with the only exception being an x in place of a y, I'm expecting my function x to have the same form as y. X of t is going to look like, now one thing I'm going to be careful about is my parameters. I'm calling this c1 and that c2. I don't want to reuse the same parameters. I'm going to call it c3 e to the 5t plus c4 e to the negative 3t. Now, I have an x and I have a y. They're general solutions, but I'm actually not done yet, because these equations up here imply that there's relationships between x and y themselves, and those relationships might actually imply that there's relationships between the parameters we're using also. In fact, the solution to this system of equations should only have 2 parameters. It shouldn't have 4. So we're going to try and figure out a way to deal with that somehow. So let's, I don't know if I have enough space in here to even do this, but we'll try. What we're going to do is pick one of our 2 original equations up here, and we're going to substitute what we have just found into that. So if I, for example, were to do that with my first equation, I need to know what dx dt is. So I can find that here. Dx dt is equal to 5c3 e to the 5t minus 3c4 e to the negative 3t. Okay, that gets substituted in for the dx dt right here. So now I'm going to have 5c3 e to the 5t minus 3c4 e to the negative 3t, and that should be equal to 4x plus 7y equals 4 times x. X was equal to c3 e to the 5t minus 3, oh no, I'm sorry, plus, I'm looking at the wrong part, plus c4 e to the negative 3t. And y, when I'm doing this plus 7y here, y we solved for right there. So that's plus 7 times c1 e to the 5t plus c2 e to the negative 3t. Okay, let's combine some like terms there. So if I distribute the 4 and the 7, I have e to the 5t showing up in a couple of places. That's going to give me 4c3 plus 7c1 e to the 5t, and then plus 4c4 plus 7c2 e to the negative 3t. Okay, now this needs to be an identity. This side should equal this side for all values of t, which means that I can equate the coefficients on these exponential terms. So for example, I have an e to the 5t here and an e to the 5t here, and coefficients on each of those. I can set them equal to each other. 5c3 equals 4c3 plus 7c1. Similarly, negative 3c4 is equal to 4c4 plus 7c2. Now what I can do is I can combine some, like subtract the 4c3 over, subtract the 4c4 over, and solve for these guys. So what does that look like when I do that? Well, if I solve these, for one unknown in terms of the other, I get c3 equals 7c1, and I get c4 equals negative c2. Okay, what that does is it creates something that I can substitute in for the c3 and c4 over here, so that both equations are in terms of just 2 parameters, c1 and c2. So my end result is this: x of t is equal to, instead of c3, I'm going to write that as 7c1 e to the 5t plus, instead of c4, I write negative c2. Let me actually change that to a minus c2 e to the negative 3t, and then y of t, I have already solved for up there, and I'll just rewrite it again down here. C1 e to the 5t plus C2 e to the negative 3t. That is my finished solution. Okay, we have one more example to look at. I'm going to do that in the next video.